Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and where knowledge drifts in gently like soft light from a distant star. Tonight's journey takes us into one of the most mysterious questions ever asked by human beings. What existed before the Big Bang? Before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if these calm explorations help your evenings feel a little softer. And when you're ready, leave a comment letting me know where in the world you're listening from and what time it is for you right now. It's always a quiet joy to see all the places we gather from, each of us held within our own little pocket of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let yourself drift into this gentle question. And if your mind wanders along the way, that's perfectly fine. Let it wander. The story will still be here, unfolding at its own unhurried pace. There's something special about the question we're opening with tonight. It looks simple on the surface, the kind of question a child might ask while staring at a night sky full of stars. What was there before the Big Bang? It feels like there should be an answer. Everything we've ever known has a beginning, a first moment, a cause, a spark. A book has its first page, a river has its source, even the day has its sunrise. And so it seems only natural to imagine the universe must have had a time before it. Another chapter that came earlier. Perhaps a darkness waiting for the first light. But as soon as we ask the question carefully, as softly as picking up a fragile object, it begins to shift in our hands. The word before, so ordinary in daily life, starts to become slippery when applied to the entire universe. Modern cosmology tells us that the Big Bang was not an explosion in space. It was the moment when space itself began to stretch. And time, that steady ticking we use to order every memory, every thought, every hope, was woven into that stretching. The universe didn't expand into emptiness. The emptiness was created as it expanded. There was no silent chamber waiting to be filled. The chamber itself was part of the event. And when physicists trace the universe back through its evolution, through the formation of galaxies, through the glow of the cosmic microwave background, through the first fractions of a second, all the way to that point we symbolically call time equals zero, the mathematics begins to tremble, equations stop behaving, numbers shoot toward infinity. The fabric of space-time, usually so predictable, folds into shapes we can no longer follow. That trembling tells us something important. We're approaching the boundary of what our current laws can describe. It's a little like walking toward a horizon. From afar it looks like a solid line, crisp and clear. But as you approach it, you realise there's no edge at all. Just more land, more sky, and a dissolving of the line you thought you were walking toward. The beginning of the universe is a horizon of this kind. We see its outline. We can walk close to it with telescopes and equations. But right at the edge, everything we know softens, and our tools no longer work as they usually do. That's why some physicists suggest that asking what happened before the Big Bang might be like walking north from the North Pole. You can take steps in any direction, but none of them lead further north, because north at that point simply stops being a meaningful idea. In the same way, if time itself began with the universe, then before may be a word that loses its footing. It's not a bad question. It's just a question that may not fit the shape of reality. But the story doesn't end there. There's a quiet courage in science, a willingness to explore even when the trail becomes faint. And so cosmologists search for clues not only in theory, but in the pale afterglow of the early cosmos. We have evidence for what happened a second after the Big Bang, a millisecond after, even a fraction of a second after. We can describe how matter cooled, how light broke free, how the first structures formed. But further back, in that incredibly tiny, incredibly energetic moment, our understanding becomes uncertain. We're missing a bridge, a way to connect the two great descriptions of nature, the smooth, sweeping geometry of Einstein's gravity and the jittery, restless dance of quantum mechanics. Without that bridge, the very first instant remains veiled. The laws we rely on to describe everyday motion, the path of planets, the bending of light, or even the behaviour of atoms simply aren't built for temperatures and densities beyond our wildest imagination. The Big Bang asks us to imagine a universe compressed into something so small and so energetic that our familiar physics unravels. And so we hover there, just shy of the moment itself, aware that something profound happened, but not yet able to say what. In this space of not knowing, imagination and mathematics work together. Perhaps time really did begin at that moment, and there was no before. Or perhaps the Big Bang was not a beginning at all, but a transition, a shift from one state of reality to another, like ice melting or water boiling. Perhaps there were earlier chapters, hidden from view but still woven into the greater story. Or perhaps time in its deepest form is not even a river, but something else entirely. Something that doesn't flow until conditions allow it. As we drift further into tonight's journey, we'll explore all these possibilities softly and patiently. The idea that time might have a beginning is staggering. The idea that it might not is equally staggering, and somewhere between these two possibilities, between beginning and no beginning, lies a quiet invitation not to find certainty, but to let ourselves sink gently into the mystery. There's a gentle moment that happens whenever you try to answer a question that sits right at the edge of human understanding. You pause as if holding something delicate in your hands, and you realise that the words you're about to use might not be built for the thing you're trying to describe. Tonight's question, what we really mean by a beginning, is just like that. It's simple in everyday life. We begin our mornings when we open our eyes. We begin a story with its first sentence. A song begins with its first note. But when we try to stretch that same idea over the entire universe, over all of space and time, the word beginning starts to wobble a little, as if suddenly unsure of itself. In our daily experience, time feels like a river flowing endlessly from one moment to the next. We're carried along by it. Memories follow one direction. Causes lead to effects. There's always something that came earlier, even if just by a heartbeat or a breath. That's why the question, what was before the Big Bang, feels so natural. It seems like the universe should follow the same pattern. Every event sitting on a timeline that stretches backwards forever. But to understand why this intuition doesn't quite work, we need to step back and look at the way physics uses the word time, which is not always the way we do in conversation. Time in modern physics is not simply a universal ticking clock. It is part of the fabric that shapes everything. When we talk about space-time, one intertwined whole, rather than separate pieces, we're saying something profound, that time only exists as part of the universe itself. It is not an external stage on which the universe performs, it's more like the rhythm of the performance, intertwined with the dancers, changing as they move, and that rhythm only exists because the universe exists. It doesn't play in the background before the cosmic story begins. This raises a surprising idea. When we ask what happened before the universe came into being, we might be stretching our language outside its natural boundaries, trying to use a map in a place where directions no longer apply. Asking what came before time might be like asking where a melody was before the first note was played. Not in a physical sense, but in a conceptual one. The melody begins with the note. There isn't a melody waiting in the silence before it. There's just silence. Even more curious is that physics gives examples where a question is perfectly reasonable in grammar but not in meaning. One of the classic ones is, "What's north of the North Pole?" The sentence makes sense in English, but in geography, the answer is that north simply stops having meaning at that point. You can stand on the North Pole and walk in any direction you like, but none of them take you further north. The concept ends there. Some cosmologists think the beginning of time might be like this, a point where the familiar meanings of earlier and later simply stop applying. But our intuition rebels against this idea, because in our lives there is always a cause behind every effect. We wake up because an alarm rings, a flower grows because a seed was planted, a question is asked because a thought arises. So when we imagine the universe, it's hard not to picture some earlier cause waiting behind the curtain, something that set the whole cosmic story in motion, a match that struck the fire, a spark before the flame. But if time itself began at the Big Bang, then the universe didn't need an earlier cause in the usual sense. There was no before for a cause to inhabit. It's a strangely liberating thought, one that removes some of the pressure from our minds, which are constantly chasing origins. But it can also feel unsettling. We're used to building chains of explanation that go back step by step. If you trace your existence backward, you find your parents, your grandparents, a long line of ancestors, and eventually the early Earth, and then the cosmos itself. And it's tempting to look over its shoulder and ask what came before. But this backward tracing eventually reaches the boundary of time, and beyond that, there might not be a scene to step into. This doesn't mean the universe popped into existence without reason. It means that the idea of reason in the sense of an earlier event may not be the right shape for this question. Instead, the conditions of the universe at its earliest moment could be seen as a kind of starting frame, a point not caused by something earlier, but simply given as the earliest moment where the laws we know begin to operate. In the mathematical sense, the Big Bang becomes a boundary condition. Instead of a fire beginning to burn, it is more like the first value in a sequence, the first point in the geometry of space-time, not caused by an earlier dot, but the dot from which the line begins. There's a quiet beauty in this perspective. It invites us to imagine the universe not as something that burst violently into existence, but as something that opened like a flower from a state where time had no meaning yet. And if time was born in that opening, then it carries with it the imprint of that first moment, an imprint we can still sense today in the expansion of space and the soft afterglow of ancient light stretched across the sky. We might never see beyond this boundary directly. We might never be able to point to an earlier moment because such a moment may not exist. But what we can do is reflect with a kind of gentle curiosity on what the word beginning truly means. For the universe, it might not be a mark on a timeline. It might be something more subtle, more geometric, more foundational, and more mysterious than the start of a counting sequence. A beginning that isn't preceded by another step, but a beginning that simply is. And as we continue drifting through tonight's exploration, we'll keep this idea close, that sometimes the world doesn't need to fit our intuitions. Sometimes the story begins exactly where the story begins, and that is enough. With that in mind, we can now wander a little deeper into what the universe allows us to see, and what remains gently beyond our reach. When you look up at the night sky, especially on a quiet evening when the world has settled into its slower rhythms, it's easy to feel as though you're seeing forever. Stars appear scattered endlessly outward, as if the universe stretches without limit in every direction. But the truth is softer, stranger, and far more intimate than that. What you see when you look into the sky is not the whole universe. It's simply the part of the universe that has had time to reach you. And this idea, the observable universe, is one of the most important keys to understanding why questions about before the Big Bang are so subtle. Light doesn't travel infinitely fast. It moves at a constant, steady pace, what physics calls the speed of light, but which we might call the universe's gentle speed limit. If a star is 1,000 light years away, its light takes 1,000 years to reach us. If it's 1 billion light years away, then we're seeing it as it was 1 billion years ago, long before humans, long before Earth, long before the solar system even existed. This means that every direction in the sky is a kind of time machine. Looking far enough away is the same as looking deep into the past. And so, when we talk about the observable universe, we're talking about the sphere of sky from which light has had enough time, roughly 13.5 billion years, to finally arrive here, to us. Anything further away simply hasn't had time to whisper its presence yet. Not because it doesn't exist, but because the universe hasn't existed long enough for that light to reach our eyes. It's as if we live in a softly expanding bubble of visibility, and beyond its gentle boundary lies a darkness that isn't truly dark, just not yet illuminated by the finite speed of light. This boundary is called the cosmic horizon, or sometimes the light horizon, and while it may sound like a hard edge, it's not a wall, not a barrier, not a place you could ever fly to. It's more like the limit of a story that hasn't finished being told. The universe extends beyond this horizon, possibly even infinitely, but we can't see it or measure it directly. And this matters deeply for our journey tonight, because it tells us that our knowledge is shaped not just by what exists, but by what has reached us. If you imagine standing by the shore of a vast ocean on a misty morning, you can only see the water out to a certain distance. Beyond that, everything fades into fog. The ocean still continues, of course. Waves still break, currents still move. But from where you stand, there is a natural limit to your sight. The observable universe is something like that. Not the totality of what exists, but the part whose light has had enough time to pierce the cosmic mist and make itself known. This limit also gives us a way to peer back into time, because the further out we look, the further back we see, until eventually we reach a kind of wall. Not a physical wall, but a moment in cosmic history where the universe was too young for light to travel freely. In that early time, everything was so hot, so dense, that light couldn't pass through without being scattered. It's a little like trying to see across a room thick with smoke or fog. Photons, the little packets of light, were constantly bumping into matter and never getting far. The moment the universe cooled enough for light to travel unhindered is still visible today. It forms a faint glow filling the sky in every direction, called the cosmic microwave background. This faint light is the oldest picture we have of the universe, a snapshot not of stars, but of the universe as a baby, still smoothing itself out, still finding its shape. When we look at that glow, we're seeing the universe as it was nearly 14 billion years ago, long before galaxies formed. It's a kind of cosmic fossil, frozen in light. But this fossil has a limit. If we look any further than that, we don't see earlier structures. We simply run out of photons that can travel to us. The universe becomes opaque, like a curtain closing off everything before it. This is another boundary, another horizon we cannot see past, not because nothing existed before it, but because the physics of that early moment didn't allow light to carry information to us. And this matters because it illustrates something subtle but profound. We live in a universe where our vision, both literal and scientific, only extends so far. Not because we lack imagination, but because nature itself has boundaries on what can be observed, at least directly. When we ask what existed before the Big Bang, we're stepping past all these horizons, past the region where light can guide us, into a territory where our usual tools telescopes, detectors, even many of our equations no longer reach. This does not mean we must stop asking, but it does mean we need to understand the shape of the unknown. Think of holding a candle in a dark room. The candle doesn't illuminate everything, it simply lights up a small sphere around you. Everything beyond that sphere is still real, it's simply beyond your reach. Cosmology is like this. Our knowledge shines into the darkness, revealing an astonishing amount of structure, history, and beauty. But the darkness remains vast, reminding us that our place in the universe is small, not insignificant, but humbled by the scale of what we cannot yet see. This limitation is not a flaw in science. It is an invitation to curiosity. It's a reminder that knowledge is always a partnership between what we can measure and what we can infer, between the evidence carried to us by light and the careful imagination guided by mathematics. The observable universe is enormous, but it is still only one cosmic neighbourhood among many possible ones. And as we drift further into our journey tonight, this idea will help us make sense of why the Big Bang looks so much like a beginning, and why it might not have been the first event in the grand story of reality. There's a moment, somewhere between wakefulness and sleep, when time loosens its grip a little. Seconds feel softer, the mind wanders more freely, and in that drifting state, the question of what time really is becomes strangely open, almost like you can feel its shape without needing to define it. This is a helpful place to be as we enter tonight's next stretch of thought, because to understand why, before the Big Bang might not exist in any ordinary sense, we need to look at time not as a clock on the wall, but as something woven into the universe itself. Most of us carry a picture of time that comes from daily life, a straight line stretching from the past, through the present, into the future. Events fall neatly along this line, one leading to the next. It's comforting, it's familiar. But in Einstein's work, this picture changes completely. Instead of imagining time as a separate thread laid beside space, he showed that space and time are a single fabric, spacetime, interwoven in a way that cannot be pulled apart. The world doesn't happen in time. Time is part of the world happening. One way to feel this idea, without any heavy formulas, is to imagine a blanket. Every point on the blanket is connected to the others. If you tug one corner, the entire surface shifts. Space-time behaves like that. When matter or energy is present, it bends the fabric. Paths curve. Light follows these curves. And time, the ticking you feel inside your mind, flows differently depending on how the fabric is shaped around you. Clocks run slower in stronger gravity, faster in weaker gravity. Not because they malfunction, but because time itself stretches and compresses with the shape of space-time. This leads to something quite astonishing. If time is part of the fabric of the universe, then the universe doesn't unfold within an existing timeline. The timeline unfolds with the universe. And that means time itself has a history. It has a beginning. It's not eternal in the way we sometimes picture it. That beginning, according to the equations of general relativity, occurs at what physicists call time equals zero, softly understood not as a raw symbol on a page, but as the earliest moment for which the equations still behave predictably. If you trace the universe backward, imagining galaxies contracting, stars unforming, atoms dissolving, space tightening, and everything becoming denser and hotter, eventually you arrive at a moment where the curvature of space-time grows so steep that the familiar mathematics fails, not because the universe explodes in chaos, but because the equations themselves reach a point beyond which they cannot describe what's happening. It's a boundary of knowledge, not necessarily a physical edge. This boundary is what we call the Big Bang, and it's here, right at this frontier, that our usual questions start to bend under their own weight. When the math is followed to this point, time appears to begin. There is no earlier coordinate, no page before page 1. No deeper layer of before, in the same sense that there is yesterday before today. For the universe, this boundary is the earliest moment where the geometry of spacetime makes sense. It is not an explosion into space. It is the moment space and time themselves emerge. To make this even more intuitive, imagine a globe. Earth seen from above. At the very top is the North Pole. You can walk south in any direction, but you cannot walk further north. The word north loses its meaning at that point. Similarly, before may lose its meaning at the Big Bang. It's not that there is a hidden stretch of time before it, it's that the concept itself stops mapping onto anything real. This is difficult for us emotionally because the mind naturally wants a cause. If something begins, we instinctively ask what triggered it. It's how we understand everything from storms to stories. But in this view of the universe, the need for a cause before the Big Bang may be misplaced, because before is not part of the structure. Cause and effect require time, and if time begins at the Big Bang, then the universe doesn't have a cause in the traditional sense. Not because it did something magical, but because no earlier moment exists for a cause to occupy. There's a quiet beauty in this kind of beginning. It's not a spark in the darkness, not a fire lighting up a room. It's more like the moment a canvas appears before a painting can begin, or the instant a melody becomes possible because the first note has been played. The fact that we can't ask about a moment before the first note doesn't mean the music is incomplete. It means the music begins exactly where it should. But even within this picture, there's a deeper mystery. If time is part of space-time and space-time can curve and stretch, then the birth of time itself is tied to the birth of the geometry of the universe. And geometry, this subtle shape of reality, might behave very differently in the extreme conditions of the early cosmos. Some physicists believe that the singularity, the point where the equations break, is not a real event at all. Instead, it's like the boundary of a map, where the picture simply doesn't continue, not because the world ends, but because the mapmaker hasn't drawn that region yet. This is why many modern theories try to push beyond this boundary. But even before we explore those ideas, cycles, bounces, hidden dimensions, quantum beginnings, it helps to sit with the idea that the Big Bang might truly mark the start of time, and that before might be a word that doesn't belong to that moment. As we drift further into this thought, it's worth remembering that our intuitions evolved to understand days and seasons, not the origins of space-time. It's only natural that questions feel strange here. But strange doesn't mean unsatisfying. Sometimes the most calming idea is that the universe does not need a cause before its first moment, because that first moment is the moment time itself becomes real. There's a gentle strangeness to the idea that the universe might not have a sharp beginning at all, that instead of a single, abrupt moment when everything burst into existence, the earliest phases of the cosmos might have been smooth, rounded, and almost dreamlike. To explore this idea, we drift into a corner of physics shaped by Stephen Hawking and James Hartle, who suggested that perhaps the most natural way to describe the birth of the universe is to imagine time behaving differently from how we usually experience it. Not flowing like a river, but curving like a landscape. Not starting with a jolt, but softening into existence the way dawn slowly lifts over a horizon. To reach this perspective, we need to take a gentle step into a concept called imaginary time. And already the phrase sounds misleading, because it doesn't mean time that isn't real or time that we merely imagine. It's more like a mathematical direction that acts differently than the time we feel passing moment by moment. The idea comes from a simple act, rotating the way we describe time so that it behaves like a spatial direction rather than a temporal one. It's called a wick rotation in technical language, but for our quiet journey tonight we can think of it in a softer way. Imagine turning a path so that it no longer runs forward and backward, but curves sideways, becoming part of the landscape rather than something you move through. In this rotated picture, time stops acting like a line with a beginning. Instead, it becomes another direction in the shape of the universe, something you can move along just as you might walk east or west. And when time behaves like this, something remarkable happens. The sharp, jagged edge that we usually call the Big Bang smooths out into a rounded region with no boundary. There's no first point where everything suddenly springs into existence. Instead, there's a gentle transition from a timeless state into the warm glow of the universe's earliest moments. To imagine this visually, think of Earth again, not the whole planet, but the surface. The globe is finite but has no edge. You can walk all around it without ever encountering a cliff where the surface simply stops. The north and south poles are special points, yes, but they are not boundaries of the surface. The surface is complete, self-contained, and smooth. In the Hartle-Hawking picture, time in the earliest universe might have been something like that surface. A smooth shape, finite in size but without a border. No before, just a rounded region where the familiar distinction between time and space hasn't fully formed yet. As the universe expands and cools, this exotic geometry slowly transitions into the kind of time we experience, time that has direction, flow, and an arrow, time where moments line up and memory forms. In this view, time with a clear before and after is not fundamental. It's something that emerges when the universe becomes cool and spacious enough for matter to settle into patterns and entropy to begin increasing. The arrow of time, its forward direction, may not exist in the earlier stage at all. Instead, the universe before that transition might be described by a geometry where the difference between past and future simply doesn't make sense yet. This idea may sound abstract, but in practice it removes one of the most troubling puzzles in cosmology, the singularity. A singularity is not a physical event. It's a sign that our equations break down like a compass spinning wildly near a magnet. By letting time curve gently into an imaginary direction, the singularity dissolves. The early universe becomes smooth rather than infinitely sharp, finite rather than infinitely dense, no point where all quantities blow up, no place where physics collapses into mystery, just a softly rounded shape that transitions gracefully and continuously into the expanding cosmos we see today. This doesn't mean the universe existed eternally before the Big Bang. It means that the very concept of before might not apply to this earliest region because time, in the familiar sense, had not yet crystallized into its directional form. It's similar to asking what the temperature of water is before it becomes ice. The question doesn't map neatly because the state you're asking about isn't defined yet. Ice has a temperature, liquid water has a temperature, but when water is halfway between states, when it is neither fully frozen nor fully melted, the question becomes blurry. The universe too may have passed through a state where time itself was not yet something that could be counted. What's profound about the no-boundary idea is that it offers a beginning without a starting point. A universe with a finite size in its earliest configuration, but without a boundary you can point to and say, it began here. It replaces the hard edge of the Big Bang with something soft, continuous, and mathematically elegant. And because the starting region is smooth, it naturally leads to a universe that is smooth on large scales, one of the puzzles that the Big Bang alone could not fully solve. This model also changes how we think about the birth of laws. If the early universe is described by a smooth, boundary-free geometry, then the laws of physics themselves may not be imposed from outside. They may arise from that geometry, the way the curvature of Earth creates predictable paths for winds and currents. In this sense, the universe's earliest moment isn't a command or a decree. It's a shape, one that gradually unfolds into the reality we inhabit. There's a quiet comfort in the idea that the beginning might not have been a violent flash, but a gentle rounding, that the universe didn't erupt into being, but blossomed out of a deeper, calmer state, where the distinction between space and time had not yet sharpened. It suggests that the deepest roots of reality might not be chaotic, but tranquil, a smooth, curved foundation beneath all the complexity we see today. And as we drift deeper into our exploration tonight, this picture offers a soft transition point. If the Big Bang was not the ultimate beginning, but rather the moment when time took on its familiar form, then the question, what was before, becomes less like a puzzle waiting for a solution, and more like a reminder that some concepts only make sense once the universe is ready for them. The idea of earlier may simply not belong to the earliest frame of existence. There's a quiet strangeness in the way time feels to us. We sense it moving, slowly during a dull afternoon, quickly during moments of joy, and with a sort of dreamy softness in the moments before sleep. We feel as if we're being carried forward, second by second, by a current we cannot see but always obey. Yet some of the deepest insights in physics suggest that this sensation, vivid as it is, may not reflect what time truly is. According to several major perspectives, the flow of time might be more like a story our minds tell us than a fundamental feature of the universe. And to understand why this matters for the question of what existed before the Big Bang, we need to explore a picture of reality that is both unsettling and strangely peaceful. One of the most influential of these ideas is the block universe view, which emerges naturally from Einstein's equations. In this picture, time isn't something that flows. Instead, the universe is a four-dimensional structure, length, width, height, and time existing all at once, like a vast landscape. Every moment we consider past, present, or future is simply a different location in this landscape. Nothing is becoming, nothing is passing. Everything that ever happens, every star born, every life lived, every thought formed, is part of this enormous structure, already laid out from beginning to end. To picture this gently, imagine a long, beautifully illustrated scroll rolled up on both ends. When you unroll a small part, that section becomes your present. The parts still rolled up are your future, and the parts rolled back are your past. But the entire scroll exists all at once. Your experience of moving along it is what gives the impression of time passing. In this view, the universe is the scroll, and your consciousness is the unrolling. This is not just poetic exaggeration. In many formulations of quantum gravity, including the Wheeler-DeWitt approach, the deepest description of the universe does not include a time variable at all. The fundamental equation describing reality in this framework has no ticking built into it, no marks of earlier or later, no direction, no momentum of moments. Instead, the universe exists in a kind of timeless state, like a vast web of possibilities. Time appears only when certain parts of this web serve as clocks for others, when matter evolves in patterns that can be compared, allowing us to define a before and after. From this perspective, time is not a universal river, it's a local experience that arises only when there is change, memory, and a way to compare one state to another. The arrow of time, its one-way direction, comes not from some cosmic rule, but from something much humbler, entropy, the measure of disorder. And this brings us to one of the most beautiful and gentle ideas in cosmology, the reason time feels like it flows forward. is because the universe began in a remarkably ordered state. Entropy tends to increase. That's why perfume spreads through a room, why ice melts, why memories accumulate in one direction. This increase gives time its arrow. But this raises a deep question. Why did the universe begin in such a low entropy state, so orderly that the arrow of time could emerge in the first place? That peculiar order is not predicted by any simple equation. It is, in a sense, a mystery encoded in the earliest moment of the universe. And this is why some physicists call the Big Bang not just a beginning, but a boundary condition, a starting arrangement so smooth and unlikely that it shapes every moment that follows. In everyday life, we think of time's direction as obvious, but imagine a deck of cards freshly sorted by suit and number. If you start shuffling it, order becomes disorder. That direction, from organised to mixed, is the natural one. The early universe was like that sorted deck. Not because something arranged it that way, but because that initial smoothness was built into the structure of space-time itself. The Big Bang wasn't simply an explosion. It was the moment when the universe began its long journey from simplicity toward complexity. This picture also changes how we think about flow. In a block universe, nothing flows. All moments exist equally. Our perception of movement through time is created by the way our minds process information, always carrying the imprint of the past but never the future. It's as if we walk through a gallery of moments, one painting at a time, never noticing that the entire gallery already exists around us. If this sounds abstract, it helps to remember that physics has shown many times that the way the world truly behaves often departs from the way it feels. We feel the Earth is still beneath our feet, even as it turns and races through space. We feel solid walls, even though they're mostly empty space. And time feels like a flow, even if the universe may be timeless at its foundation. Now you might wonder, if all moments exist at once, what does that mean for the Big Bang? In a block universe, the Big Bang is not the first moment in the sense of one event causing the next. It's a special region of the space-time landscape, a place where the fabric is extremely compressed, extremely smooth, and extremely young compared to the parts that come later. It's like the narrow end of a valley that widens as it stretches outward. There is no before in the sense of events happening earlier. There is only the structure itself, complete and self-contained. This doesn't mean the universe didn't emerge from anything. It means that emergence and unfolding might not be the right words. The universe may simply be a shape in 4 dimensions, stretching from its earliest moments to its farthest, and our experience of moving through it is a kind of internal journey, a story told by consciousness as it travels along the path laid out in the geometry. This idea doesn't answer everything. It doesn't tell us why the universe has the shape it does, or why time appears the way it does. But it gives us a new perspective, that the beginning of the universe might not be a point sitting at the end of some earlier timeline, but a feature of a larger whole, a whole that doesn't need a before, because time itself is part of its structure. As we drift into the next chapter of our journey, this view will help prepare us for models where the Big Bang is not a beginning at all, but a transition, a bounce, a cycle, or a transformation. But before we explore those ideas, take a moment to rest in the thought that time, as real as it feels, may be one of the most delicate illusions the universe creates. There's something deeply comforting about the idea that the universe might breathe, that instead of beginning in a single, unreachable moment, it moves through vast cycles of expansion and contraction, like an ancient lung slowly inhaling and exhaling across unimaginable stretches of time. Tonight, as we drift deeper into our quiet exploration, we turn toward this gentle possibility that the Big Bang may not have been the first chapter of everything, but simply the latest turning point in a much older rhythm. To ease into this idea, imagine standing on a quiet shore and watching a tide come in. Waves rise, stretch, and then draw back, only to gather again and return. If you only saw one wave in your entire life, you might think the ocean is defined by a single forward motion. But when you see many, the pattern becomes clear. Some cosmologists wonder whether we've only seen one cosmic wave, one expansion of spacetime, and mistaken it for a unique beginning. Perhaps, long before the moment we call the Big Bang, the universe was already engaged in a kind of cosmic breathing, each breath expanding into a universe much like ours. In some classical cyclic models, the universe grows for billions of years until its expansion slows, stops, and then reverses. Space contracts. Galaxies draw closer. Stars collide and die. Everything becomes denser and hotter until the entire cosmos is compressed into a state far smaller and stranger than anything we can easily imagine. And then, instead of collapsing into a singularity where the laws of physics break down, the universe rebounds. It bounces. And that bounce becomes the Big Bang of the next cosmic cycle. In this view, the universe is not a one-time event, but a vast, ancient heartbeat. But as simple and poetic as this image feels, the physics beneath it is subtle. For one thing, our universe today is not slowing down, it's speeding up. The discovery of cosmic acceleration surprised astronomers in the late 20th century, showing that galaxies are rushing away from each other faster and faster, driven by something we call dark energy. In a universe like ours, one that accelerates, there's no obvious path toward contraction. The expansion simply continues, stretching space farther and farther until galaxies slip beyond one another's horizons. So classical cyclic models had to evolve. The modern versions don't imagine an endless expansion that suddenly reverses. Instead, they imagine stages, periods of growth and periods of rebirth, triggered not by gravity pulling everything back, but by the deeper geometry of space-time or by fields that behave differently under extreme conditions. In these models, the bounce doesn't come from the universe falling back in on itself like a collapsing balloon. It comes from the idea that space-time has a kind of elastic quality at very small scales, preventing it from shrinking to a true point. This brings us to one of the biggest puzzles of any cyclic universe: entropy. Entropy is often described as the measure of disorder, but it might be easier to picture it as the tendency for things to mix, spread out, and become less organised. Think of an ice cube melting into water, or a freshly sorted deck of cards being shuffled. Over time, disorder grows, and in our universe, entropy has been rising since the Big Bang, giving time its direction. But if entropy grows with every cycle, then each cycle of the universe should be more disorderly than the last. Eventually, the cycles should become so chaotic that they cannot reset into the next. This was the problem that haunted early cyclic models. If the universe has been cycling forever, then where did all the entropy go? Modern cyclic theories offer soft, elegant answers. One influential idea by Paul Steinhardt and Neil Turok imagines that during the transition between cycles, the universe undergoes an extraordinary geometric transformation that stretches space so dramatically that entropy becomes diluted, thinned out like a tiny drop of ink spread across a vast ocean. In this picture, each cycle begins fresh, not because entropy disappears, but because the conditions of the bounce scatter it into insignificance. Another way to resolve the entropy issue is to imagine that the cycles are not identical. Perhaps each new universe is larger than the previous one, with more room for entropy to disperse. Or perhaps the fields and dimensions that drive cosmic evolution operate in ways we do not yet fully understand, allowing each cycle to begin with a smoothness that naturally resets the arrow of time. And there is yet another layer of beauty in cyclic models. They naturally explain why the universe looks so uniform on very large scales. When we look out across billions of light years, we find that opposite sides of the cosmos have nearly the same temperature, even though light has not had time to travel between them since the Big Bang. Inflation, a rapid early expansion, solves this puzzle in the standard model, but cyclic universes solve it differently. If the cosmos has been expanding and contracting for ages, then distant regions of the current cycle could have been neighbours in a previous one, sharing information long before our Big Bang occurred. In that sense, the smoothness of the universe, the calm, even glow we see in the cosmic microwave background, might be a whisper from an earlier cosmic era. But perhaps the most profound aspect of cyclic universes is the emotional one. There is something deeply human about the idea of cycles. Our days are cycles, our seasons are cycles, our lives, even with all their twists and unique paths, follow rhythms we see echoed in nature. A cyclic cosmos mirrors these patterns on a scale beyond imagination. It suggests that the universe is not a fragile one-time event, but a resilient, enduring sequence of rebirths. And yet, even if the universe cycles, we must still ask, where did the first cycle come from? Is there a true beginning? Or has the universe always existed in one form or another, breathing endlessly in ways we're only beginning to glimpse? As we continue wandering through these possibilities, we'll see that cycles are only one kind of pre-Big Bang universe. The next possibilities drift even deeper. Quantum bounces, ancient aeons, universes budding inside black holes, and realities connected across time by hidden dimensions. Each of these offers its own answer, not final but inviting, about what may have existed before or perhaps beyond the moment we call the beginning. There's a special kind of quiet that comes when you imagine the universe at its smallest, so small that the concept of size itself becomes hazy, almost poetic. A universe compressed into something tinier than an atom, smaller than any particle we've ever measured, and yet holding within it the seeds of everything: stars, galaxies, oceans, memories, entire civilizations that will one day wonder where it all began. Tonight, in this soft stretch of our journey, we turn toward a possibility that lives at this minuscule scale, that the universe did not begin from a point of infinite density, but instead passed through a moment of minimum size, rebounding gently from a contraction into a new expansion, a cosmic bounce, shaped not by classical physics but by the strange, subtle rules of the quantum world. To feel this idea intuitively, imagine a child's trampoline. If you press down gently with your hand, the fabric resists at first. Push harder, and it stretches. Push even harder, and it pushes back. But no matter how hard you press, there's a limit. The fabric won't let you go through. According to many proposals in quantum gravity, space-time behaves in a similar way. Under normal conditions, it bends and curves smoothly, following Einstein's equations. But when squeezed to extreme densities far beyond what stars or black holes ever reach, space-time becomes elastic in a quantum sense. It resists collapsing into a true point. Instead of forming a singularity, it rebounds. This is one of the central insights behind loop quantum cosmology, a theory that applies principles from loop quantum gravity to the entire universe. In this framework, space-time is not a continuous fabric, but a weave of tiny quantum loops, each unimaginably small. Under everyday conditions, these loops blur together and create the smooth geometry we're familiar with. But when the density of the universe becomes immense, the discrete nature of this weave becomes important. It prevents the fabric from tearing or shrinking to zero. Instead, the universe bounces. In this picture, the Big Bang was not the first moment of time, but rather a transition. A moment when a previous universe, contracting under its own gravity, reached its smallest volume and then began to expand again. Not with a violent explosion, but with a quiet, unstoppable push from the underlying quantum structure of spacetime, a kind of resilient rebound. What's remarkable about this scenario is that it turns the singularity, that old troublesome point where physics normally breaks down, into something understandable. Not a breakdown, but a turning point. Not an end, but a hinge. And yet, the quantum bounce is only one of several pre-Big Bang possibilities that transform the early universe into something smoother and more continuous than classical physics suggests. Another comes from the work of Roger Penrose, whose conformal cyclic cosmology proposes not just a bounce, but an endless chain of cosmic eras, what he calls aeons, each stretching from an early, fiery beginning to a cold, dilute future, and then softly transforming into the beginning of the next. In Penrose's picture, the far future of the universe becomes strange in a very gentle way. As the universe expands, galaxies drift apart, stars burn out, and black holes slowly evaporate through the faint glow of quantum radiation. Over incomprehensibly long stretches of time, everything cools toward a state where particles lose their identity and the passage of time becomes meaningless. In this ultra-dilute future, only the shape of space-time remains. And because this shape no longer distinguishes between scales, there are no rulers, no clocks, nothing to measure. Penrose imagines that this scale-free future can be smoothly reshaped into the beginning of a new universe. It's as if the universe, after living its long life and wearing itself thin, fades into a kind of elegant simplicity from which a new Big Bang can naturally arise. No singularity, no abrupt beginning. Just a soft bridging between the final moments of one aeon and the first moments of the next, like two waves touching along the surface of the sea. A particularly poetic aspect of Penrose's idea is the possibility that traces of earlier aeons might linger in the cosmic microwave background, the faint afterglow of our own universe's earliest light. He suggests that certain circular patterns or subtle imprints could be the footprints of massive events that happened before our Big Bang, perhaps collisions of supermassive black holes in a previous aeon. Whether these imprints truly exist is still debated, but the idea itself is beautiful, that our sky might carry whispers from a universe long gone, a message passed across cosmic cycles. Both the quantum bounce and the conformal cyclic view share a gentle theme. They replace the abruptness of a beginning with the continuity of a process. Instead of a universe conjured from nothing in a single flash, reality becomes a long, unbroken story. Each chapter flows into the next. Each era inherits some of the structure, or at least the potential, of the one before. The cosmic story becomes not a single arc, but a series of breaths, a rhythm stretching backward into a past we may never fully see. These ideas also offer a new way to think about our cosmic identity. If the universe has passed through many cycles, then each Big Bang might be less like a creation and more like a renewal, a resetting of conditions, a rearrangement of the cosmic canvas, giving rise to different possibilities each time. Stars burn differently. Galaxies assemble differently. Perhaps laws themselves shift slightly, exploring new patterns across each aeon. In such a universe, we're not the audience of a one-time performance. We're the latest refrain in a cosmic song that has been humming for ages. As comforting as these scenarios can be, they come with a quiet humility. Even if the universe has cycles, even if there were earlier eras, we may never access their details directly. The bounce might erase almost all traces of the previous universe. The transition from one aeon to the next might smooth over everything but the faintest hints. Our instruments and equations can offer glimpses, echoes perhaps, but the full story may remain forever beyond reach, folded into the geometry of time itself. Still, something about these models resonates deeply. They allow us to imagine a universe where the Big Bang is not a hard wall but a doorway, not the first moment, but a moment in a chain, and in that chain we can sense continuity without losing the wonder of beginnings. A beginning that is not absolute but still precious, a beginning that marks the dawn of our particular cosmos, even if many dawns came before it. There's a special kind of feeling that comes when we think about black holes, a mixture of awe and unease, as if we're watching the universe fold its secrets into a dark, quiet room with no windows. They are places where gravity becomes so powerful that not even light escapes, where time slows, stretches, and finally seems to stop at the event horizon. But tonight, as we settle deeper into our soft exploration, we'll consider a possibility that is as astonishing as it is gentle, that inside every black hole there might be a new universe beginning to unfold, and perhaps, long ago, our own universe began inside a black hole tucked within a larger parent cosmos. To ease into this idea, let's start with a simple image. Imagine a seed, small, dense, unassuming. From the outside it looks like nothing much, but inside it, folded quietly, lies the potential for forests, for shade and shelter, for entire ecosystems. A black hole might be something like that, a seed whose interior is not compressed into nothingness, but expanded into something vast. In the familiar picture of a black hole, space curves inward so steeply that once you cross the event horizon, the boundary of no return, everything falls inevitably toward the centre. Classical physics describes that centre as a singularity, a point where density becomes infinite and our laws fail completely. But as we've already seen with the Big Bang, a singularity in the equations often means not that reality breaks, but that our understanding does. In fact, many modern theories suggest that the interior of a black hole may not collapse to a point at all. Instead, it may continue as a new region of spacetime, branching off from the parent universe, expanding in its own direction. To picture this softly, imagine the event horizon as a shell. From the outside, the shell appears dark and closed, but on the inside, it might be a doorway into a new expanding space, a universe with its own timeline, its own stars, its own galaxies. In this picture, a black hole is not just a trap, it's a tunnel. And what appears to be an ending from one side becomes a beginning from the other. This idea arises naturally from the equations of general relativity when they are extended beyond the simple picture of collapse. If we treat the extreme curvature inside a black hole not as a death point for physics, but as a region where the geometry transforms, we discover that the interior may have room to inflate. The inward fall becomes a kind of bounce, driven by the same quantum effects that soften the Big Bang singularity. And once the geometry begins to expand on the inside, it can blossom into a full universe, with space growing rapidly, so rapidly that the connection to the parent universe becomes hidden behind the event horizon. In this model, the event horizon of the black hole becomes the Big Bang surface of the new universe, and the singularity becomes something like a memory of the collapse that birthed it, a relic of the past smoothed out by quantum processes. From inside, the new universe doesn't see a black hole. It sees an expanding cosmos full of potential. The newborn universe is unaware of the parent, and the parent universe, from the outside, sees only a black hole, quiet, dark, swallowing matter, yet perhaps creating something entirely new within. One of the most beautiful aspects of this scenario is that it offers an answer to one of the oldest puzzles in cosmology: why the universe is so smooth at large scales. If our universe began in the collapse of a star-sized region in a parent universe, then the enormous compression leading to the bounce could have wiped away most of the irregularities, much like kneading a piece of dough until it becomes uniform. The new universe begins with a fresh, even texture, which later expands into the large-scale uniformity we observe today. But the idea goes even deeper. If universes can be born inside black holes, then each universe might pass on certain traits to its offspring. The physical constants, the strength of gravity, the charges of particles, the masses of fundamental ingredients might shift slightly from one generation to the next, just as traits shift through biological evolution. This leads to a provocative possibility. Universes that produce many black holes might become more common over cosmic timescales, not because they are chosen, but because they reproduce more efficiently. In that sense, the cosmos could be evolving. Universes that are better at creating black holes create more children, each with a slightly different set of laws, and over unimaginably long stretches, the most common universes are the ones whose physics naturally favours black hole formation. It's a quiet, cosmic analogy to natural selection, not in biology, but in the architecture of reality itself. Of course, this idea is still speculative, but it carries a kind of poetic symmetry. Stars form, live, and collapse into black holes, and inside those black holes, new universes might form, grow, and evolve. A cycle not just of stars but of entire worlds, connected through hidden passages of space-time. The emotional resonance of this idea is powerful. It means that the universe is not a solitary entity, alone in the dark. It may be part of a lineage, one universe born from another, and ours perhaps giving birth to others still. Every black hole we observe might be the cradle of a new cosmos, quietly unfolding its own history behind that dark veil, and our own universe, so vast and ancient, may itself be the interior of a black hole formed in some older reality. As we continue through tonight's journey, this idea adds another soft layer to our exploration of before. It suggests that beginnings and endings might be linked, that collapse and creation might be two sides of the same motion, and that perhaps, when a black hole forms somewhere in the cosmos, the universe is not losing something. It may be gaining something we simply cannot see. If you close your eyes for a moment and picture nothing, you might imagine a blank silence, an empty room without walls, without air, without light, a stillness so complete that even the idea of motion feels out of place. This is how we tend to picture the void: quiet, featureless, utterly empty. But tonight, as we drift deeper into the soft underlayers of cosmology, we step into one of the most surprising discoveries of modern physics, that what we call nothing may actually be one of the most restless, energetic, and creative states in the universe. In quantum field theory, the framework that describes the tiniest ingredients of reality, empty space is never truly empty. Even when you remove every particle, every atom, every photon, what remains is not a quiet vacuum, but a shimmering sea of possibility. Fields stretch across the universe like invisible blankets, and these fields can never be perfectly still. They quiver with tiny fluctuations, brief flickers of energy that appear and vanish too quickly to be directly observed, like sparks in a dream. These flickers are often called virtual particles, not because they are imaginary, but because they arise and fade before we can register them with our instruments. They are part of the quantum background hum, the heartbeat of nothingness. To feel this idea gently, imagine a perfectly still lake at dawn. From afar it may seem motionless, but if you watch closely, you'll see tiny ripples forming and fading, stirred by currents too subtle to notice until you look carefully. The vacuum of space is like that lake. What looks calm from far away is alive with small bursts of motion. One of the clearest proofs of this unseen activity is something called the Casimir effect. But instead of introducing it with symbols or technical language, we can picture it with something simple. Two mirrors placed very close together. If you bring two mirrors face to face with only a thin sliver of space between them, the fluctuating fields around them behave differently inside that narrow gap than outside it. And because the vacuum outside the mirrors holds slightly more restless energy than the vacuum inside, the mirrors are gently pushed toward each other, as if the nothingness between them is thinner or quieter than the nothingness surrounding them. It's a small effect, but it's real, and it shows that empty space is not empty at all. This restless vacuum opens up a remarkable possibility that a universe, our universe, might have emerged from one of these tiny fluctuations. Not from a true absence, not from philosophical nothingness, but from the quantum fabric itself, which is never fully still. In this scenario, a small region of the vacuum experiences a momentary rise in energy. Instead of fading away like most fluctuations, this one tunnels into a new state, a state where space-time can expand. A new bubble appears, tiny at first, but growing, stretching, and eventually becoming a universe with stars, galaxies, planets, and minds capable of wondering where it all came from. This idea may sound magical, but it rests on a gently surprising principle. The total energy of a universe can be effectively zero. Matter, everything with mass, carries positive energy. Gravity, however, carries negative energy. And if the positive energy of all the matter balances the negative energy of gravitational attraction, the universe can have a net energy of zero, like a bank account where every deposit is matched by a withdrawal. This makes it possible, at least in theory, for a universe to emerge without violating any cosmic bookkeeping. In this picture, the universe didn't need an external trigger. It didn't need a spark from outside space-time. It simply arose as a natural possibility within the quantum vacuum, the way a bubble might form spontaneously in a pot of water just before it boils. The laws that govern the vacuum allowed such a bubble to exist long enough to grow, and once growth began, cosmic inflation, a rapid, early expansion that we'll explore soon, stretched that bubble into the vast cosmos we inhabit today. But while this story is soothing in its simplicity, it carries a deeper, quieter question beneath it. If the universe came from the vacuum, then where did the vacuum come from? If the vacuum is a field with structure, restless with activity, then what gave rise to that structure? What set its rules? What shaped its possibilities? When physicists say nothing, they rarely mean absolute emptiness. They mean a vacuum state defined by laws, fields, and the potential for fluctuations. This is not the philosophical nothing of pure absence. It is a fertile nothing, a structured nothing, a canvas whose texture is rich enough to produce universes. This distinction matters because it reminds us that even the simpler sounding explanations carry mysteries of their own. A quantum vacuum capable of birthing universes is not a trivial thing. It is a deeply organized state, full of hidden symmetries and potentials. If the universe came from such a vacuum, then the origin of everything becomes the origin of those deeper rules. Some perspectives suggest the vacuum might be eternal, part of a timeless background that exists without need for further explanation. Others propose that even the vacuum might be emergent, arising from deeper layers of reality we have not yet glimpsed. And then there is the possibility that our concept of origin itself breaks down when we try to dig too deeply. much like how the idea of before time dissolves when time itself begins. What the quantum vacuum offers us is a gentle bridge between nothing and something, a way the universe could arise naturally, quietly, without needing a moment when a literal nothing suddenly became everything. It paints a picture not of creation ex nihilo, but of transformation, a fluctuation becoming a cosmos, a ripple becoming a sea, a moment of quantum possibility blossoming into stars and life. As we drift toward the next part of our journey, we will see that this quantum beginning is only one possibility, and that the universe may have grown not only from a fluctuation, but from a brief, astonishingly rapid stretching of space-time known as inflation. But for now, it is enough to rest in this idea that nothingness may be far more alive, more textured, and more generous than we ever imagined. If you imagine the universe in its very first moments, you might picture something chaotic, a wild, churning storm of particles and light, clashing in a rush of unimaginable heat. But one of the most surprising insights in modern cosmology is that the universe did not begin in chaos. Instead, it seems to have begun in extraordinary smoothness, like a sheet pulled perfectly flat, or a lake whose surface reflects the sky with hardly a ripple. How did a universe filled with so much complexity, so many galaxies, so many stories, arise from something so calm? To find the answer, we drift tonight into the idea of inflation, a moment in the universe's early history when space expanded not just quickly, but with a speed and gentleness that reshaped the entire cosmos. To ease into this possibility, imagine holding a slightly wrinkled piece of cloth. If you pull gently at its edges, the wrinkles stay. But if you stretch it suddenly and powerfully, almost faster than you can follow, the wrinkles vanish. The fabric becomes smooth. Inflation is like that powerful stretch, an expansion so swift that any irregularities in the early universe were stretched out of existence, leaving behind a cosmos so uniform that even opposite sides of the sky shine at nearly the same temperature. Before the idea of inflation emerged, physicists struggled with a puzzle called the horizon problem. When we look at the cosmic microwave background, the faint afterglow of the early universe, we find that regions of the sky extremely far from each other have nearly identical temperatures. Yet these regions are so distant that, according to the normal expansion of the Big Bang, they should never have been close enough to exchange heat or information. They should be strangers with different stories, but instead they match. Like two people raised on opposite sides of the world telling the same childhood memory, their similarity seems too perfect to be accidental. Inflation provides a soft, elegant answer. Before inflation, the universe was tiny, so tiny that every region could share information and settle into a smooth state. Then, in a fraction of a moment, space expanded faster than any speed we normally describe, not because anything moved faster than light, but because the fabric of space itself stretched. This stretching carried once neighbouring regions so far apart that they became the opposite ends of our sky. Their similarity isn't a coincidence. It's a memory of their closeness before inflation whisked them away from each other. It's important to pause here and say gently, when we talk about inflation expanding faster than light, we're not describing objects racing through space at impossible speeds. Instead, the space between them grew. It's like dots on a balloon that drift apart as the balloon expands. No dot breaks any cosmic rule. The surface beneath them simply stretches. This is one of the subtle beauties of inflation. It reshapes the universe without violating the gentle speed limits built into space-time. Inflation also helps solve another puzzle called the flatness problem. If the universe had been even slightly curved in its earliest moments, curved like the surface of a sphere or the saddle of a horse, those curves should have become more pronounced over time. But when we measure the universe today, its geometry appears almost perfectly flat, like a sheet of paper. Inflation explains this by stretching out any initial curvature the way a huge map stretches a small patch of Earth. A balloon inflated to the size of a planet would look nearly flat on any small area. And inflation did something even more dramatic. It stretched the cosmos so much that its curvature became too faint to detect. But what caused inflation? What drove space to expand in such a peculiar and powerful way? The idea is that a special kind of field, often called the inflaton field, filled the early universe. Unlike fields we're familiar with, such as electromagnetism, this field had a kind of stored energy that remained nearly constant for a brief moment. That constant energy acted like a pressure pushing outward, forcing space to grow at an astonishing rate. And when inflation ended, the stored energy of the field transformed into particles, heat, and light, filling the young universe with the ingredients that would eventually form stars and galaxies. This moment is called reheating, but we don't need to think of it as a furnace. It's more like the universe exhaling after holding its breath. What's astonishing is how small the universe was before this stretch began. The entire observable universe, everything we can see today, was once smaller than the smallest speck we can imagine. Smaller than any grain of dust, any particle, any point of reference from daily life. A region so tiny that you could not see it with any microscope, even a hypothetical one that could peer into quantum scales. And yet this tiny region, expanded by inflation, became everything we know. Every galaxy, every atom, every moment of history came from that minuscule patch of spacetime stretched into immensity. There is something deeply humbling about this thought. It means the vastness around us, the 100 billion galaxies, the 100 billion stars in each, may all have begun as a whisper of space, so small and so simple that its details were erased in the act of expansion. Inflation took something humble and made it grand. It took a tiny seed and unfolded it into a universe. But inflation also sets the stage for ideas even more astonishing. If the inflaton field drove expansion in our universe, it might have done so unevenly. In some regions, inflation may have ended, allowing universes like ours to form. In others, it may still continue. This leads to the idea of eternal inflation, where space becomes a foam of universes, bubbles within bubbles, each with its own story. Before we drift into that possibility, it's worth pausing to appreciate inflation itself. It is not simply a theoretical trick. It is a deeply elegant solution to puzzles that once seemed contradictory. It ties together smoothness, flatness, and the size of the observable universe with a single, gentle concept: stretching. And like many of nature's most beautiful ideas, it is both surprising and intuitive once it settles into the mind. In the next phase of our journey, we'll float from this single stretch into a vast sea of possibilities, a multiverse born not from one expansion but from many. But for now, let the idea of inflation rest softly in your mind, like the memory of a balloon rising into the quiet air. There's a moment in every great story when the world suddenly becomes larger, when a door opens or a curtain lifts, and what you thought was everything turns out to be only one room in a vast mansion. Tonight, we arrive at that moment in our cosmic story. Because once we accept inflation, the rapid stretching of space in the earliest fraction of a second, it becomes almost impossible to ignore a quiet but astonishing possibility. That inflation may not have stopped everywhere, that our universe might be just one bubble in a much larger cosmic sea, and that beyond the edges of what we can see, countless other universes may be blooming, each with its own laws, its own patterns, its own quiet beginnings. To understand this, imagine for a moment that the inflating space-time of the early universe is like rising dough. When dough rises, it expands everywhere, but it doesn't rise uniformly. It forms pockets of air, little bubbles where the dough gives way to something hollow. In eternal inflation, the universe behaves in a similar way. The underlying field that drove inflation in the first place may decay in some regions, allowing expansion to slow down and matter to form. But in other regions, the field keeps its energy and continues to stretch space. These pockets where inflation ends become bubbles, isolated universes like ours, floating in a larger inflating background. In our bubble, inflation stopped long ago, space cooled, particles formed, stars ignited. Life eventually learned to ask questions. But in the larger landscape, inflation may still be raging on, endlessly stretching the regions between bubbles. And in that relentless stretching, new bubbles keep appearing, universes budding off like blossoms from an infinite vine. Each bubble is sealed away from the others, not by walls but by the fabric of space-time itself. The distances between bubbles grow so quickly, and the space between them expands so fiercely, that any attempt to travel from one to another becomes impossible. Even light, the fastest messenger in the universe, cannot cross the gulf. Each bubble becomes its own cosmos, with its own timeline, its own history, and its own potential for complexity. This idea is known as the multiverse, not as a speculative fantasy, but as the natural consequence of inflation allowed to continue indefinitely. The mathematics of inflation, when extended gently into the deepest regimes, suggests that once inflation starts, it never stops entirely. It may end in our region, but continues elsewhere forever. That's why it is called eternal inflation. Inside each bubble, the physics may look familiar, or not at all. The properties of our universe, the strength of gravity, the charges of particles, the structure of atoms, might be determined by the way our bubble formed. Another bubble might have a slightly different set of properties, just as two snowflakes born in the same cloud take different shapes. Some bubbles might be inhospitable to life, others might be chaotic, and some may never form stars or galaxies at all. But among the vast, endless foam of possibilities, there will inevitably be bubbles where conditions are right for complexity to bloom. This leads us to the idea known as anthropic reasoning, which sounds complex but has a gentle truth at its heart. We observe a universe where life is possible, because only universes that allow life can ever be observed by beings like us. It's not an explanation in the traditional sense. It doesn't tell us why the universe has its particular laws, but it reminds us that when looking across an infinite landscape of universes, we should not be surprised to find ourselves in one where stars can shine, planets can orbit, and consciousness can arise. It's simply the kind of bubble where observers can exist. This doesn't make our universe any less meaningful. In fact, it can make it feel all the more precious. One delicate bubble where the laws are just right for atoms to build stories, for light to ripple through space, for creatures to wonder about their origins. Some physicists even suggest that bubble universes might collide occasionally, like soap bubbles drifting across a basin. If two bubbles brushed against each other in the distant past, the collision could leave a faint imprint, a circular scar in the cosmic microwave background. Scientists have searched for such patterns. They've found hints, suggestions, anomalies, but nothing yet that stands as clear evidence. Still, the possibility is tantalizing. The idea that the sky might hold subtle memories of ancient cosmic neighbors. Another striking feature of eternal inflation is its fractal nature. As inflation continues in some regions while ending in others, the overall structure of reality becomes a repeating pattern. Expanding space dotted with bubbles, each bubble containing galaxies below galaxies, each galaxy containing stars below stars, each star containing atoms below atoms. A cascading architecture. The closer you look, the more structure you find, and the deeper you go, the more the pattern repeats. Reality in this picture is not just endless, it is endlessly creative, and yet, despite the vastness of this multiverse, our bubble remains complete in itself. Everything we know, every star we can see, every galaxy that shines in our telescopes, every memory you carry, belongs to this one region of space-time. The existence of other bubbles doesn't diminish ours. They don't touch us or affect us. They simply expand the possibilities of what reality might contain. There's a soft humility to this perspective. It suggests that the universe is not centered on us, not even centered on our bubble. We are one story among many. But that doesn't make our story any less beautiful. It simply means the cosmos has more room for wonder than we once imagined. As we drift into the next chapters of our journey, we'll see that this multiverse, vast and foaming with possibilities, might itself be only a layer, sitting atop deeper structures like hidden dimensions and branes. Each idea opens another doorway, another quiet question. But for now, let the thought settle. Our universe may be one bubble in a sea of bubbles floating in the endless night. There's a moment when you gaze into a mirror facing another mirror and see reflections folding into reflections, a soft corridor of images stretching into the distance. Each reflection is slightly changed, a little dimmer, a little narrower, but clearly connected to the one before it. The deeper you look, the quieter it feels, as if the world is repeating itself in smaller and smaller whispers. Eternal inflation creates something a little like that. Only instead of reflections, it's universes. Instead of mirrors, it's space-time unfolding endlessly. And instead of a corridor, it's an infinite sea. Tonight we drift into that sea. We've already explored the idea that inflation may continue forever in most regions of space-time, forming bubble universes where it briefly stops. But if we look at this process carefully, softly, without rushing, we discover something even more astonishing. It doesn't just produce a collection of universes, it produces a structure, a pattern, a cosmic architecture that repeats at different scales, the way coastline patterns repeat whether you look from a mountaintop or with your feet in the sand. This is the fractal nature of eternal inflation. To imagine it gently, think of tree branches spreading outward. Each branch splits into more branches, and each of those splits again. Look from afar, one tree. Look closer, a forest of miniature trees nested inside one another. The universe, according to this picture, might be growing in a similar way. Regions of space expanding, producing bubbles, and within some of those bubbles, quantum fluctuations creating smaller regions that expand anew. The pattern repeats and repeats, not because the universe tries to mimic fractals, but because the underlying rules of inflation naturally create them. In this picture, the multiverse isn't a static gallery of universes suspended in some vast blackness. It's a living process, a growing thing. A foam that constantly produces new bubbles even as old ones drift further apart. Space itself becomes a self-replicating canvas, painting new patches as fast as it expands. No matter how far you zoom out, there are always more bubbles forming, more space stretching, more branches splitting from old ones. The cosmos becomes an endless fractal bloom. And if this is true, it changes something subtle about how we make predictions. In a single universe, ours, we're used to the idea that the laws of physics let us predict many things with certainty. We can tell when a planet will orbit, how a pendulum will swing, how light bends around a star. But in a fractal multiverse, where every possible arrangement of physical constants might appear somewhere, certainty becomes softer, probability becomes essential. Imagine standing at a crossroads where many paths branch out in every direction. To predict the future from that point is no longer about identifying one exact path. It is about describing which paths are most likely, which are rare, which dominate the branching. In a fractal multiverse, this kind of reasoning becomes central. We no longer ask, what must the universe be like? We ask, among all the universes that exist, what kinds are most common, and what kinds allow beings like us to emerge? Some people find this uncomfortable. It feels like physics giving up on certainty, but this isn't a retreat, it's a shift in perspective. If the universe is not a single timeline but a branching process of endless possibilities, then statistical prediction, gentle, probabilistic, humble, is the natural language to describe it. For example, in many versions of eternal inflation, universes like ours, where matter is stable, stars shine for billions of years, and chemistry has the subtlety needed for life, are not necessarily the most common. They may be rare blossoms in an enormous garden of strange exotic possibilities. But from within such a universe, we of course see conditions that allow our own existence. We observe laws that permit atoms, molecules, and thoughts, because only such environments can host observers capable of noticing anything at all. This is anthropic reasoning, but in the fractal multiverse, it becomes a quiet, almost obvious reflection of where we stand. And yet, this fractal sea invites a deeper philosophical question, one we can approach softly, like stepping into a warm pool at night. If everything that can happen does happen somewhere, what does it mean for us to predict anything? Does science lose its grounding? The answer is calmer than it first seems. Even if every possible universe exists, not all universes are equally common in this branching structure. Some are like rare pearls, others are like grains of sand. The task of science becomes identifying the patterns of universes that arise most often, the typical outcomes of the cosmic branching process. Predictions shift from "this must happen" to "this is overwhelmingly likely," which in a universe as vast as ours is often more than enough. And there is another gentle comfort hidden here. Even within a multiverse of endless possibilities, our universe is still uniquely ours. It's not replaced by others. It's not diminished by their existence. In a garden filled with countless flowers, one blossom does not lose its beauty. It simply shares the world with many others. This fractal perspective also sets the stage for a new idea, that perhaps this branching sea of universes is itself only one layer of reality. Beneath it, or alongside it, deeper structures may exist, hidden dimensions, floating branes, sheets of reality drifting through a higher dimensional space. Perhaps the branching of bubble universes is just one ripple in a much larger ocean. Before we step into that ocean, it's good to rest for a moment in this one. The multiverse may be vast, recursive, endlessly creative, but here, in the middle of that fractal bloom, is a simple truth. The universe you experience, the one filled with memories, warmth, curiosity, and quiet evenings, is one of the rare places in this immense cosmic foam where consciousness can arise. And that makes it special, no matter how many other universes may exist. There is a particular kind of wonder that comes from imagining hidden layers beneath the world we see. As children, many of us suspected secret rooms behind bedroom walls or hollow spaces under the floorboards, places where something magical might be waiting, unseen but present. In modern cosmology, something remarkably similar appears. The possibility that our familiar universe, its stars, its galaxies, its flowing time, is just one surface inside a larger, richer reality with more dimensions than we can perceive. A reality where universes drift, ripple, and sometimes collide like great cosmic sheets. To ease into this idea, imagine holding a sheet of paper. From far away it looks perfectly flat, two-dimensional, with only length and width. But if you bring it close, you notice its hidden thickness. You can bend it, fold it, twist it. That tiny third dimension may be nearly invisible from afar, but it exists, influencing everything the sheet can do. Physicists suspect that our universe may be like this sheet of paper, a three-dimensional brane floating inside a higher dimensional space called the bulk. And just like the paper, our brane may hide dimensions that folded up so tightly in the early universe that we can no longer see them. These ideas come from string theory and its larger relatives, frameworks in which the fundamental ingredients of reality are not point-like particles, but tiny vibrating strings. These strings require more than the 3 dimensions of space we know. They need 9, or 10, or sometimes 11 dimensions to vibrate correctly, the way a violin string needs the length and tension of its instrument. We only notice 3 spatial dimensions because the others may have curled up on themselves in the earliest instance after the Big Bang, like tiny loops tucked into the structure of every point in space. In this picture, our universe is like a surface within a higher dimensional ocean. Most of the forces we know, light, electromagnetism, nuclear interactions, are stuck to our brane. They cannot leave. But gravity is different. Gravity is gentle, subtle, and willing to slip through cracks. According to some models, gravity can seep into the extra dimensions of the bulk, like water trickling through porous stone. This may explain why gravity feels so weak compared to other forces. We feel only the small portion that remains on our brane, while the rest spreads into dimensions we cannot access. Now imagine that we're not alone in this higher dimensional space. Just as many sheets of paper can sit side by side in a stack, many branes may drift through the bulk. Some might be parallel to ours, some might be curved, some might have very different properties, carrying different versions of physics, different kinds of matter, or even different arrows of time. These branes need not interact most of the time. They can drift for eons without touching. But sometimes, gently or violently, they might collide. And here is where the idea becomes extraordinary. In some theories, the Big Bang was the result of such a collision. To picture this softly, imagine 2 enormous sheets floating in a quiet ocean. For ages they drift apart, carrying their own hidden landscapes. Then, after a long wandering, they slowly brush against each other. The contact releases enormous energy that, from within one sheet, would look like a sudden, hot, brilliant beginning. From our perspective inside a brane, this collision would appear as the birth of our universe, a sudden release of heat, an expansion of space, a dramatic moment that feels like a beginning, even if something existed before it. This view is part of what's known as ekpyrotic cosmology. In this model, the Big Bang is not an origin but an event, a transition caused by 2 branes touching. The expansion we see is the result of that impact echoing across our brane, and before the impact, time may have flowed quietly in the bulk, meaning the real before existed, just not inside our universe. Hidden dimensions offer another gentle twist. During the earliest phases of the universe, some dimensions may have behaved differently from others. Some may have been large, like the spatial dimensions we experience today. Others may have curled up and frozen into tiny loops no larger than the dust motes floating in a sunbeam. In this view, the Big Bang was not the universe appearing out of nothing, but a moment when dimensions took on different roles. Some stretching outward to form the space we move through, others collapsing inward into structures too small for us to detect. This phase transition picture of the early universe replaces the idea of creation with the idea of transformation. It's like the moment water freezes. Not a disappearance of water, but a reorganization of its structure. The Big Bang becomes the moment space-time solidified into its familiar shape. These possibilities also shift how we think about our cosmic loneliness. If other branes exist, they might hold their own universes, ones we can never reach, but that drift beside us in the bulk like ships crossing at a distance through a fog. Their stars, if they have them, would not shine in our sky. Their gravity might tug faintly across dimensions, but no more. They are separate worlds, not just far away, but sealed off by the fabric of reality itself. Yet the emotional resonance of this picture is soft and profound. It suggests that our universe might not be the only story unfolding. There may be countless branes drifting silently through higher dimensional space, each carrying its own version of reality, its own timeline, its own wonders. And our Big Bang, far from being the first light ever kindled, may be one spark among many, one branch of a larger unseen cosmos. As we continue our quiet exploration, this idea opens one more door. If our universe is a brane, and other branes exist, and the bulk holds all of them, then the structure of reality might be even richer than the multiverse we imagined earlier. Inflation may create bubbles within a brane, while hidden dimensions hold branes within a larger space. Reality becomes layered, textured, endlessly deep. But before we move on, let this thought settle gently. The universe you know, the one filled with galaxies and starlight, may be only one sheet drifting in a vast cosmic stack. There's a certain quiet that settles over the mind when you begin to wonder whether reality, this world of sunlight, memories, emotions, distant galaxies, and the gentle ticking of your own thoughts, might be built from something deeper than matter. Not something mystical, but something structured, something shaped, something like code. Tonight, as we drift softly into one of the most provocative ideas in modern philosophy and cosmology, we'll explore the possibility that our universe could be a simulation, not a cartoonish video game or a crude digital model, but a deeply intricate reality produced within a larger hidden framework. It's important to begin gently. The simulation hypothesis is not about denying the reality of your experiences, quite the opposite. It says that if a world is detailed enough to give rise to conscious beings who can love, fear, learn and wonder, then that world is real for those who live in it, no matter how or where it is implemented. A simulated pain is still pain. A simulated joy is still joy. A simulated universe, if rich enough, is still a universe. The idea most famously enters mainstream discussion through philosopher Nick Bostrom, who suggested a simple but powerful trilemma. Either advanced civilizations do not survive long enough to create simulated universes, or they survive but choose not to simulate conscious worlds, or they do simulate many worlds, and if they do, then simulated beings would vastly outnumber biological ones, making it likely that we ourselves are among the simulated. You don't need to accept any of these possibilities with certainty to feel their weight. They each describe a different path for intelligent life, and the last of them opens the door to an extraordinary possibility that the laws of physics we observe are not the ultimate laws, but the rules of a deeper computational layer, not digital in the sense of bits and bytes floating on a screen, but computational in the sense that reality follows consistent instructions, updating in time the way a vast simulation would. To feel this idea softly, imagine looking very closely at a photograph. If you zoom far enough, the smooth colours dissolve into tiny squares, pixels. Each one holds a little piece of the picture. You don't notice them at normal scale, but they form the foundation of the image. Some scientists wonder whether space and time might be like that, smooth at our scale, but granular at the smallest. Perhaps there is a smallest tick of time, a smallest distance, a smallest bit of information that reality never subdivides beyond. Not because nature needs to work this way, but because a simulation must work this way, everything built from fundamental steps. In this context, the speed of light, the ultimate cosmic speed limit, begins to look like a kind of refresh rate. Not an arbitrary constraint, but the maximum pace at which information can move across the grid of reality. And the smallest moment of time, often called the Planck time, begins to resemble a universal clock cycle, the smallest heartbeat in the computation underlying existence. These analogies are not perfect, but they provide a quiet way to imagine why the universe behaves with such precise consistency. Quantum mechanics, too, takes on a different texture under this interpretation. When we observe a quantum system, the act of measurement changes the system. Before measurement, many possibilities coexist. After measurement, one outcome becomes real. Some physicists compare this to a rendering engine in a simulation, a system where details are computed only when needed. Just as a video game generates scenery only when the player looks at it, reality might generate specific outcomes only when an observer interacts with the quantum world, not because the universe is hiding something, but because this is the most efficient way to run a complex simulation. Compute only what is relevant. It's important not to stretch this analogy too literally. The universe is not a pixelated video game built to entertain us, but these gentle comparisons help make sense of why the universe has a maximum information speed, why space appears smooth yet may be discrete, why quantum events seem to choose outcomes only when observed. These features may reflect the architecture of a deeper layer of reality, whether or not we call it a simulation. Another quiet suggestion from simulation-based thinking is that there may be many universes, not just bubbles born from inflation or branes floating in higher dimensions, but simulated worlds produced for any number of reasons: scientific curiosity, historical recreation, exploration of possibilities. If a civilization ever reached technological maturity, with the ability to create rich simulated environments, they might run countless simulations, each one with different initial conditions or physical laws. From within one, it would be impossible to know how many others exist, or whether there are layers upon layers of simulation above your own. Yet even within this dizzying vision, there is a kernel of calm. Whether our universe arises from a quantum vacuum, a brane collision, a bounce from a previous cycle, or a simulation created by beings in a higher reality, the lived experience does not change. The night sky remains full of stars. The warmth of a hand held in affection remains real. The gentle satisfaction of understanding something new remains true. The simulation hypothesis also invites one more quiet reflection. Even if the universe is code, where did the coders come from? What set the rules of their world? What lies beneath that layer? Every explanation, whether physical or computational, leads us back to the same boundary of understanding, the same horizon we keep approaching. The simulation hypothesis broadens our imagination, but it doesn't escape the deep mystery of origins. It simply shifts the question one level up, like moving a light from one shelf to another without illuminating the whole room. As we drift into the next phase of tonight's journey, this idea gently prepares us for a more philosophical turn. Because whether or not we are simulated, we face the same ancient question: can every why eventually be answered? Or does the universe contain questions that softly resist resolution, not because they are beyond intelligence, but because they dissolve when we try to ask them? There comes a point in every long journey when the road ahead begins to fade into mist. You can still walk, still breathe, still feel the air on your skin, but the landscape becomes softer, harder to grasp. Tonight, as we drift through the penultimate part of our exploration, we arrive at that misty edge, the place where scientific questions blur into philosophical ones, and where the very language we use begins to lose its footing. We often imagine that every well-formed question must have an answer. From childhood, we are rewarded for asking why, and the universe seems full of reasons waiting to be uncovered. But as we explore the idea of what existed before the Big Bang, or whether before even makes sense, we reach a boundary where the usual rules of questioning begin to bend, like tree branches leaning under a heavy snowfall. To ease into this, imagine standing at the North Pole. If someone asked you to walk north, you would have nowhere to go. The question is grammatically correct, perfectly understandable, yet physically meaningless. It's not that the North Pole refuses to answer. It's that the question points outside the structure of the world. Many cosmological questions behave this way. What happened before time began? Maybe one of them. If time is not a stage on which the universe plays, but a property of the universe itself, woven into space-time like threads into cloth, then asking what happened before time is like asking what sound a colour makes. Not wrong, just misaligned with the nature of things. Physics, at its heart, is the art of building models, mathematical structures that describe how the universe behaves. These models can be tested, refined, and sometimes replaced. But every model rests on assumptions. Every model defines its own boundaries. And every model, when pushed too far beyond its valid range, begins to give answers that sound like nonsense, not because they're profound, but because we're asking more of the model than it can deliver. For example, general relativity works beautifully at large scales. It describes the bending of starlight around galaxies, the expansion of the universe, and the warping of space near black holes. But when we push it to the earliest moments of the Big Bang, it predicts a singularity, a point of infinite density and zero volume. Infinite values in physics are often signs that a theory is being stretched past its domain of usefulness. It's the universe's quiet way of saying, you need a deeper model here, something quantum, something with granularity, something that replaces the sharpness of infinity with the softness of possibility. Quantum mechanics, in turn, works perfectly well for atoms, molecules, and subatomic particles. It gives probabilities instead of certainties, gentle distributions instead of strict outcomes. But when we try to use quantum mechanics to describe the entire universe, its origin, its total state, we again reach the edge of what the theory can comfortably hold. The equations describing the wave function of the universe sometimes lose their interpretation, as if we're trying to read a map of a place where the idea of direction no longer applies. All the models we've explored, cyclic universes, quantum bounces, multiverses, brane collisions, simulations, extend the chain of explanation one step further. They soften the singularity. They add structure where previously we believed nothingness to be absolute. They give us beautiful and imaginative ways to think about origins. But each one, when questioned too hard, eventually ends with its own version of "we don't know." Consider the quantum vacuum model. It says the universe may have arisen from a fluctuation in a restless sea of energy. But where did that sea come from? Why does it have the laws it does, and not others? If we say the vacuum simply exists eternally, we've given an answer of sorts, but not one that satisfies the deeper why. Cyclic and bouncing models suggest the universe has no beginning at all, only transitions. But where did the cycle itself come from? Where did the rules that govern the bouncing originate? Again, the question slips into a territory where the usual tools of physics cannot reach. Brane models suggest our universe was born from the collision of higher dimensional surfaces. But why were there branes to begin with? Why does the bulk have the structure it does? And who or what wrote the rules of that geometry? The simulation hypothesis suggests our universe may be code running on a deeper computational substrate. But then we must ask, where did that substrate come from? And if the beings running the simulation live in their own universe, what explains their beginning? All paths lead to the same quiet clearing, a place where the final why remains unanswered. This is not a failure of physics. It is a reminder that the universe is under no obligation to fit neatly inside human intuition. Our minds evolved to navigate forests, rivers, and social bonds, not to unravel the ultimate structure of reality. And yet, through mathematics, imagination, and careful observation, we've managed to illuminate vast stretches of the cosmic landscape. We've traced light from the earliest moments. We've measured the whisper of the cosmic background. We've mapped the expansion of the universe and watched stars die in distant galaxies. But at the edge of understanding, the universe becomes softly elusive. Questions that feel meaningful in everyday life begin to dissolve. We approach concepts, time before time, space outside space, laws arising from nothing, that stretch language beyond its comfort. At this edge, words stop behaving the way we expect them to. They creak under the weight of meanings they were never built to carry. Instead of frustration, this boundary can be a place of peace. The fact that our understanding has limits does not diminish the beauty of what we can know. It invites humility. It invites wonder. It opens space for mystery. Not the kind that frightens or frustrates, but the kind that makes the night sky feel larger and more comforting. As we prepare to drift into the final session of tonight's journey, we hold on to this gentle truth. Not all questions need answers, and some of the most important ones may never have them. The universe is vast enough to contain mysteries we can't solve, and soft enough to let us rest within them. There is a special kind of quiet that settles in the heart when a long journey draws near its end. Not the silence of emptiness, but the soft stillness that follows understanding. Tonight, as we reach the final stretch of our exploration, we turn toward a gentle truth. We may never know whether the universe had a beginning in any traditional sense, and yet even without a final answer, we can still find meaning, comfort, and wonder in the world that surrounds us. Throughout our journey, we have wandered through many possible histories of reality. We have seen universes that bounce, collapsing inward only to rebound into new eras of expansion. We have drifted through cosmic cycles in which one aeon gives way to another like waves touching on a quiet shore. We have stepped through quantum vacuums that shimmer with restless energy, birthplaces where tiny fluctuations might blossom into entire universes. We have followed inflation into vast seas of bubbles, each one a cosmos unto itself. We have imagined dimensions curled into tiny loops, brainies drifting through a higher dimensional ocean, and collisions that ignite new universes like sparks between cosmic sheets. We have even considered the possibility that our universe is a simulation, a meticulously crafted world built atop deeper layers of reality. Each model was a different way of avoiding a hard, singular beginning. Each offered a different vision of before or beyond or beneath. And yet, as we examined each one, a pattern emerged. Every attempt to explain the origin of everything left something unexplained. Every story ended with a deeper question. If the universe bounced, what shaped the first cycle? If the vacuum birthed our cosmos, what shaped the vacuum? If brains collided, who placed the brains in the bulk? If our universe is code, who wrote the rules of the system? And if there are infinite universes, what does origin even mean? These questions are not failures. They are reminders that the universe is vast, not just in space, but in concept. They show us that the idea of a single, neat beginning might be a comfort rooted in human storytelling, not a feature of the cosmos itself. Perhaps the universe does not fit into a simple narrative with a tidy first chapter. Perhaps reality is more like a growing forest than a book, a place with roots that run too deep for any one story to trace to their end. There is something deeply reassuring about this. It means we're not expected to know everything. It means that mystery is not a flaw in the universe, but one of its most beautiful qualities. Even the most advanced theories, the ones written with exquisite mathematics, leave room for silence, for what cannot be captured by equations or words, and in that silence there is space for us. For as much as we've discussed the vast scaffolding of reality, the bubbles and branes and vacuums and simulations, the truth is that your own experience is its own kind of universe. The rhythm of your breath, the way light fills your room in the morning, the memories you carry, the questions you whisper to yourself at night. These are as real as any galaxy, as meaningful as any cosmic cycle. The grand scale of the universe does not diminish them, it magnifies them, because despite its size, the cosmos contains a moment small enough for you to exist within it. We often ask where the universe came from, but rarely pause to appreciate that we are part of that question. You're made of atoms forged in ancient stars. You're shaped by a history that stretches back billions of years. And whether the universe began with a bounce, a collision, a fluctuation, or something far stranger than we've imagined, the fact remains, the universe arranged itself in such a way that you are here, listening, breathing, wondering. In the calm of the present moment, the origin of the universe becomes less pressing. What matters is that the laws of reality, whatever their ultimate source, have allowed complexity, consciousness, and curiosity to take root. That alone is astonishing. That alone is enough. Perhaps this is the quiet lesson of living in a universe without a final origin story. The lack of a definitive beginning does not take away meaning. It gives meaning room to grow. It frees us from the expectation that the universe must revolve around a single moment of creation, a single cause, a single reason. Instead, it invites us to see the cosmos as an open field of mystery, a place where questions can be as beautiful as answers. So, as we bring this journey to a close, take a slow breath and let the vastness settle gently around you. Let the uncertainty become a soft blanket rather than a sharp edge. Let the unknown feel like a horizon at dusk, wide open, full of possibility. You're here, in this moment, part of the universe trying to understand itself, and that perhaps is more profound than any origin we might imagine. Thank you for wandering through these questions tonight. Whether your eyes are still open or drifting into sleep, may the mystery of the universe feel like a quiet companion, one that stays with you long after the journey ends.